indeed high-level speakers that will be quite stimulating what we will hear this morning. The objective of this event is to make visible what chemistry and especially catalysis will contribute to the future world, where we all hope that will be a world without the use of fossil input. And so we have to talk about what usually is called decarbonization of different sectors, like mobility, but also industrial sectors, specifically the chemical industry. Presently, we primarily rely on petroleum, but as I said already, we are looking forward and hope that we will see a society which is not dependent anymore on that. But we will be dependent on carbon. That's the reason that we don't like the term decarbonization, but we prefer defossilization. When we talk about such a future world, we still need technologies, we need input, which is, of course, dependent on electricity, electricity from renewable sources, carbon-free, but we will have chemicals available and will have fuels available. And as I said already, they will contain carbon in many cases. So the carbon will most probably come from CO2, and we will make use of electricity to produce hydrogen, which will be the other important input for the conversion of the CO2 to, let's say, hydrocarbons for fuels or chemicals. And when we talk about electrolysis, we also talk about catalysis. Electrolysis does not work without the catalysis on the electrode surfaces. And when we talk about the conversion from CO2 and hydrogen to chemicals and fuels, we also have to talk about catalysis. So catalysis definitely is the key technology for such a future world. And we will hear today something about electrolysis. That will be Rüdiger Eichel. Jens Nørskov will talk about ammonia production. Ammonia is one of the most important chemicals in the future, but maybe also important for the transport of hydrogen. Maybe he will also talk about that. And at the end of the session, we will hear about what will be the way, the roadmap to transfer our society, our industrial world, and that will be presented by Florian Ausfelder. But I have the honor to start with the fourth speaker of today. In fact, Peter Dröll will show us what's the opinion of the European Commission on this process of transfer of the society. Of course, he will talk about the Green Deal, I assume. Peter Dröll is currently the acting director of the Directorate General for Research and Innovation of the European Commission. He co-authored the Innovation Union in 2010, and he was responsible for many important aspects and activities, and among others, just to name one, he was head of the cabinet of the Science and Research Commissioner Janez Potočnik. So I'm very much looking forward to your presentation, Peter.
Thank you very much, and thanks for the nice welcome. Let me see whether I can do this with my slides here. Yes, no, that's too fast. Yeah, thanks a lot. My structure is very simple. I will briefly explain the overall context for this key technology, as you just said, catalysis, and in the transition towards sustainability, and then come to some opportunities, research and innovation opportunities at the European level. So this is a wonderful slide, I think, coming from an economist, Kate Raworth, who has written a book about 21st century economics. And her insight is that we need to steer all our economics thinking and system in a way that we respect, and that's the outer ring of the donut, the boundaries of our planet, while securing the basic needs of every individual on the planet. That's the inner circle. And the current situation quite clearly is that we are overshooting. We are not respecting the boundaries of our planet, the resources. Fossil CO2 emissions are fossil energy sources. CO2 emissions are an important factor in that equation. And we are not able to meet the basic needs around the globe for everyone. And this is the basis for the United Nations Sustainable Development Goals. And we have a very insightful report from the European Statistical Office, Eurostat, which is not enough known. And you see here the summary of the findings. And this shows that we are overall as EU, so 27 member states, making reasonably good progress. We are not so good as regards industry, certainly not so good as regards climate action, quite obvious, but also sustainable production and consumption. And this is important for chemicals. We're making some progress, but not enough. So this is another element of the context I wanted to share with you, and I recommend this report to anyone who is interested in the overall picture on sustainability. You mentioned, Wagemann, you mentioned Green Deal. This is something extraordinary. I'm for quite some time now working for this beautiful project of European integration. I've never seen a commission being able to define one overarching project, which is so well known by so many people, not just the inner circle of policymakers, and accept it. This is the overarching policy, and what is very important as well is that it has not changed due to the pandemic. Actually, all the recovery and reform plans we have and the programs member states are now preparing are based on that Green Deal objective. So we are building back, but we are building back better the economy. And here you see that this is not against growth. You see the upper chart is GDP, although GDP is a very imperfect measure for that. But you see that every sector, and on the slide it's the green sector, which represents industry, needs substantial reductions in order to achieve our overall target of climate neutrality. Now, this is a bit about the challenge. In such a chart, it looks quite easy, this circularity. As a matter of fact, it is all but easy to achieve. And it is super complex. We need better understanding still on life cycle assessment, some basic things, but it's also about behaviors. It is about regulation. It's about authorizations. If I think of reusing waste gas from industry to another one, the question of pipelines comes and authorization for pipelines. And we know how difficult it is, because also there's a question of, are we transparent enough? Do we have the acceptance of those individuals concerned by it? So the challenge is substantial, huge. And Wagemann, you mentioned that you don't like, and I fully understand that, the notion of decarbonization, because we need carbon. I hope it's a bit more acceptable if it's combined with recarbonization, because my plea here is that we need to take the carbon out of the primary energy supply, but also to recarbonize it, the emissions, and that's, I think we will hear from about this much more in the presentations after me. We need to use it as a feedstock, to recarbonize it for basic chemicals or synthetic fuels.
This term is new for me. I like it.
Oh, good. So let's come to the opportunities. And here, this is something which is running now. And I hope today there will be new interested participants in this call. It's substantial. We are intending to fund 2 projects in a volume of 40 million. And the deadline is still running, 26 January. So the background for this is that we took we proved quite flexible at European level. I have to do a bit of self-praise because we put aside 1 billion euro for COVID-related research as of March this year. And we managed to save the 1 billion euro we had set aside for the Green Deal call, for the Green Deal challenges, already under the current existing program, which is called Horizon 2020. So we maintained that, and that shows how important the Green Deal remains also for research innovation, obviously, in the pandemic. So this is an action which is important because it shows also the way how we will work in the future program Horizon Europe, which is co-created. We have discussed the core conditions, the challenges with quite a wide range of stakeholders in order to make sure that it fits best. And this is our intention also for Horizon Europe. So what is at stake? The challenge is really to convert CO2 emissions from industrial processes into synthetic fuels or chemicals using renewable energy-driven processes with novel and highly optimized energy efficient catalytic systems. And here, this is the focus of this morning's conference. The scope is to deploy and to develop and deploy highly innovative recyclable catalytic material systems to facilitate the production of synthetic fuels and chemicals from industrial flue gas, and that could be CO2 mainly, but it could also be carbon monoxide or hydrogen. And we aim at a 50% increase in the overall efficiency compared to the current state of the art. That's a bit of a breakthrough, I think, a nice challenge to crack. And it should end up at a rather high level of technology readiness level, so tested in a real environment. So that is a nice opportunity ahead. I'll come very briefly to the opportunities in the future where I cannot be that concrete because we don't have the program yet. We don't have the final agreement on the EU long-term budget yet. We hope to be able to start in next spring with the next calls under this new program Horizon Europe. Here you see that the political background is the industrial policy, the Green Deal, of course, and the digitization. We have, and this is part of the new approach, identified with the European Parliament, with member states, with a wide range of stakeholders, our key strategic orientations which shape the program. And you see them here. It's a bit complex. So what we need to remember it's about open strategic autonomy. It is about restoring our ecosystems. It is about the sustainable economy. And this is the sustainability focus and resilient, inclusive, democratic societies. This is the shortcut for these are the 4 overarching objectives for our investments, our portfolio of investment, research, innovation under Horizon Europe in the next 7 years. And part of this is one element of this, one part of the program is digital industry and space. In our jargon, we call it Cluster 4. So you see here our vision and ambition for this cluster. And it really is about the open strategic autonomy, sustainable economy, and also inclusive society. And here you have an overview of the expected impact we want to achieve. This is important to understand. We will start every investment with a reflection of what is the expected impact, the sphere of influence we want to have. The sphere of control of a project is a bit lower level, but here you see what we want to achieve. Yeah? Leadership, for instance, leadership in clean and climate neutral industrial value chains. All very relevant for this morning's discussion. And as regards catalysis, I mean, we have not finalized this program. We are just about to draft it but we have a reasonably good idea what we could have for catalysis under the overall objective to make it by design for industrial sustainability. So we will have more investments, as you see here, on the development of energy efficient, electrically heated catalytic reactors, materials, new catalytic materials, the community for solar fuels and chemicals, and also actions on hydrogen storage. This is an indication. Yeah, not yet a final promise, but you can be reasonably sure that we will continue to invest in this key technology, catalysis. And we're building on past projects we have funded. Here is just one MAPSIN, which is quite successful, and I think some of you are involved in that as well. So we are not starting from scratch, and yeah. We rely on you to make it happen because you are the actors for that. Thank you so much. Over to you.
Peter Dröll, thank you very much. That was a real great beginning, framing or describing the topic in the political framework, but also mentioning important subjects where you expect from us that we will contribute for a sustainable industrial world. And as I said already, that was really great. And thank you for being with us. And what I should have said at the beginning, that all these questions which might be now relevant, that would be the possibility to address to our speakers in the second part of the session after the break, where we have a panel discussion, but we will have a close interaction with you, the people outside there, and Peter will be with us. So I think you will be ready for quite a lot of the questions. Thank you again. You mentioned fertilizing with wind. That was on one of your last slides. I think that's the perfect transition to introduce also Jens Nørskov. In the catalysis world, I don't have to introduce Jens. He's very famous. He's the theoretician with respect to heterogeneous catalysis, with a lot of very important contributions. He's a professor at the Technical University of Denmark, and I should, among many other things I could mention, I just would like to mention that he presently is the chair of the Danish National Research Foundation. I assume a very important position, also compared to situation in Germany. Jens, we are now very much looking forward fertilizing with wind or ammonia production. Thank you for being with us.
Thank you very much for this kind introduction. Can I just, to whoever is responsible, I actually don't see the big screen of the presentation. I just see 10 small screens. I don't know if it's just my computer, but
I have the same problem, Jens.
Anyhow, probably somebody needs to make sure we only see one screen. Anyhow, let me get started here. As was mentioned already, I mean, our starting point is that everything that defines modern life today in terms of the way we transport ourselves, we've talked about fertilizers, we're talking about materials, even pharmaceuticals, all of these products that define modern life, they come today from fossil resources, as indicated here. And I think the transformation of these fossil resources into everything that we are using today has been a fantastic victory for science and for chemistry in the last century. I mean, over that 100 years, we actually learned how to transform oil products and gas into all of these products. And as we all know, we just need to get a new way of doing that. And what it means is that, let's see if this works. There we go. We need to be able to make all these products, but now using energy input from the sun in photovoltaics or wind or hydro for that matter, in order to do this. So we need a new revolution, chemical revolution, enabling this. Now, I'll be talking about that. I'll use ammonia, making ammonia from nitrogen as an example, but essentially everything that I'm talking about is very general to this whole process. Now, here's the dream device. It's a device where on one electrode, we split water to make oxygen. The protons go through a membrane and we pull the electron through, and that's where the energy input from power sources like solar or wind comes in. And then at the other electrode, either we reduce the protons to make hydrogen, or we reduce carbon dioxide to make hydrocarbons and oxygenates, or we reduce nitrogen to make ammonia. And all of these are things that we would like to be able to do very efficiently. Here's the problem. The problem is that the splitting of water, even with the best catalysts we know today, is very inefficient. So we really need, as we also heard Dr. Dröll say, we actually need a breakthrough in order to make this possible. We cannot just scale up what we have and hope that we'll get something that will be give prices of energy and chemicals even close to what we're used to from fossil resources. That's problem number one. If we look at making, reducing CO2, there we also have catalysts, but they're even worse. And if we talk about making ammonia by reducing N2, they are the worst we have. So there is an enormous challenge here. Making hydrogen is something we're pretty good at, but remember, we first need to split water. And we are very good at making hydrogen, but we're not good at splitting water. So even making hydrogen is difficult to do efficiently today. We can do it. There are industrial electrolyzers that can do this, but with a fairly low efficiency. And that's what we're up against here. Now, this is just summarizing what I said. Now, if we can make hydrogen, then we can also then make a traditional catalytic process, thermal catalytic process, to transform the hydrogen into CO2 by reacting with CO2 to make hydrocarbons or oxygenates, or transforming it into ammonia by reducing N2. This we can do today. The problem there is that what the industrial processes that have been optimized over the last 100 years for this, they are based on very large facilities. They are at high temperatures, high pressures, but if the energy comes from solar or wind, we actually don't need centralized facilities. Perhaps we need to be able to produce these things where they're being used and not where we have the energy. And therefore, we also need a transformation of these kinds of the technologies. We would not like an ammonia reactor running at 150 bar out in the barn of a farmer who wants this for making fertilizer. So we have some scientific and technical challenges here as well. So let me take you through a little bit of the science here, just to illustrate what we're up against. And I don't want to get into any details. This here, for those that are interested, is the potential energy diagram for making ammonia. And I don't want to get into the details. I just want to illustrate to you that it's complex. There are many processes, many activation energies in the problem. In fact, there are something like 14 different energies that you need to optimize at the same time in order to optimize this process. This has been done empirically over the last 100 years, starting with Haber and Bosch and Mitage exactly 100 years ago, or almost exactly 100 years ago. But how do we think about this? And I just want to suggest to you that there are actually ways of doing this. It turns out that there's really not 14 independent variables in this problem. There's only of the order 1. If we choose the right one, the right descriptor, then we can actually take experimental data shown on top, or do theory as shown below, where we can get a very systematic view of what it takes to make the best catalyst. And you can see here that if we plot rate, which is shown here on the y-axis, as a function of this descriptor, which is just a nitrogen adsorption energy on the catalyst surface, then we have an optimum where ruthenium, as you can see, is closest to the optimum that comes out of both theory and experiments. That's the best catalyst we know. It's not being used, actually. Today, it is essentially only iron which is used, and that's not because it's the best, but it's because it's cheap, dirt cheap. So we can actually project this 14-dimensional problem into a one-dimensional problem. And the key to this, without going into much detail, is that there are dependencies of all the different energies in the problem on this one particular energy. So these scaling relations that were discovered here is the key in order to reduce this complexity as much as I indicated. Now, when we have this, then we have a route to optimizing even further. And I'll just give one example here. To the left, you see what you saw before, rate as a function of this descriptor. You see ruthenium at the top, iron is not nearly as good. You see molybdenum is even worse than iron. Cobalt is much worse than ruthenium. They are on both sides of the optimum, this volcano. And if you can combine the two, you can see, then you actually get right at the top. So we can actually use the insight to begin to design catalysts on the basis not of trial and error, but actually on the basis of insight and computer modeling. And the result is shown here. If we combine cobalt and molybdenum, you actually get a catalyst, and that's shown experimentally to the right. These are experiments done at the Haldor Topsøe company. And you can see that iron is not nearly as good as ruthenium, and this cobalt molybdenum intermetallic with a little bit of nitrogen actually is as good, or under some circumstances better than even ruthenium. It's not nearly as cheap as iron still, so iron is still being used, but this is to illustrate that we can actually, if we understand well enough what is going on, we can actually begin to design catalysts in this way. Now, here's a much worse problem, or perhaps an interesting opportunity. What I'm showing here is a two-dimensional plot of rate, and this is now rate for our model. And it's a heat map so that red is high rate and blue is as low rate as possible. What I'm showing here is the rate as a function of two different descriptors. One is related to the activation barrier for splitting the NN bond, and the other is this bond energy of nitrogen. Not so important in this context. You can see this linear relationship. Each of the elemental metals, metal catalysts are shown there, and you can see this linear relationship between these two descriptors. So when you just try and optimize catalysts by trying different combinations, all you do is you run up and down this line that I'm defining there. The problem is that the real optimum is way off the line. So these nice scaling relations that made it so simple for us to optimize also defines actually what is the biggest hurdle for something much better. That is, we actually need to get off these scaling lines. And therefore we need completely new ways of designing catalysts that has this property. We need more functionality. That's what this says. And I don't want to get into the too many details of this, but actually, again, you can begin on the computer to play around. And there are, as indicated by these dots here, we can actually, on the computer, design sites that are, or surfaces that are much more active. The problem is that they're not stable. And therefore, we need to become much smarter, not just at designing these, but also at synthesizing them and stabilizing them. So there's a big amount of challenge here. Now let me turn to the other option. This was the option of making hydrogen and then using that hydrogen in a thermal reactor to make ammonia. What if we try to reduce nitrogen electrochemically? And we are up against the same problems as before. This is, again, one of these heat maps of rate or something, something related to the rate, I should say, to be exact here. And you can see an optimum, and you can see that the known materials for catalysts, for electrocatalysts here, are way off the optimum, just like before. And there's an even worse problem. And that is that if we look at different materials and look at the rate of making ammonia, which is the lower curve here, and compare to the rate of making hydrogen, because you have protons coming in. They have the choice of reacting with each other to form hydrogen or reacting with nitrogen to form ammonia. And you see the rate for making ammonia is much, much higher. This is a logarithmic scale. So we are up against the fact that the catalysts we have are way off optimum, and those that we have make hydrogen and not ammonia. And so we have some real design problems here. And this is why, as I mentioned earlier, this is the process where we are furthest away from doing anything reasonable. Let me try and illustrate here and just focus on the figure. I'm not going to go into the math. We really need to think very differently about how we control this. And one of the issues is that we actually need to be able to control the rate at which protons arrive at the surface. If we get too many protons in immediately, then you form hydrogen. If you get the protons in slowly, then nitrogen can get onto the surface and then you'll make ammonia. Instead of controlling the number of protons coming in, we can actually also perhaps control the number of electrons coming in. That's what nature does in the enzyme in nitrogenase. There's actually a very, very clear control of electrons coming in, and that's why you can make ammonia in plant or in the enzyme with a high efficiency. And I'll just illustrate this in the next plot. This is sort of a summary of where are we. This is a summary of experimental reports, and there are many, many coming out now. Most of them are probably wrong because not enough checks have been made. You can see here that there are different, if you can see it, I can't, but I remember what's on there. There are different symbols about whether in these experiments, they have made line tests or they have made isotope tests to make sure that the ammonia made comes from the nitrogen coming in. But the long and the short is that only the filled symbols, which have a high efficiency and a reasonable rate, they are the ones at the top. And they are ones where we are in an aproduct solvent, that is where we have low excess of protons, just confirming the model that I showed to you earlier. And in fact, there's really only one system where real good experiments have shown that this is a sustainable system. By sustainable, I mean one where other people can make the same experiments and get the same results. Now, this is actually an interesting system. It uses lithium as the catalyst, and you run the reactor by actually depositing lithium, just like you do when you charge a battery. And then the nitrogen reduction takes place at the surface there of this lithium. And it's an idea that actually goes back to the 30s, and then it was forgotten. Then it was rediscovered in the 90s and then forgotten. And now a number of groups have actually gotten in and really shown that this is something that works. And it works. It has an efficiency of something like 20% if you just try and do this, which is orders of magnitude better than anything else. Still a very low energy efficiency. The problem is that you can do this for a while, but then it becomes unstable. That's not so strange because you have to deposit lithium continuously, and obviously that lithium will stop being there. So you need to do something else. It's not scalable. And
Jens, I like very much your presentation, but you should come to the end. Sorry.
I'm there now. I just want to show that you can actually, there are strategies now where we can get now close to 40% efficiency, and we can really begin to do this. So there's hope. I just want to thank those that make sure that those who did the work are thanked here, but just make the point again that there are challenges on scale up of these processes, and this is not just for ammonia. This is also just for making hydrogen. But underneath that, there are actually some scientific challenges that should not be forgotten, because I see a lot of test facilities being built, including from the Commission, funding from the Commission, but I don't see any much interest in actually solving the underlying problems. And so this is my recommendation, that we really get on with the science in parallel to the scale up. Both are needed. Thank you very much.
Yeah, thank you very much, Jens. Thank you for describing so precise where the challenges, where the problems are. But at the end, we could get an imagination how progress could be. So I would say, Jens, you gave us hope. And you will be with us also during the discussion. I think there will be quite a lot of questions. Let me switch to the next expert, the leading expert on electrochemistry here in Germany, Rüdiger. Thank you for joining us. Rüdiger Eichel is scientific director of the Institute for Energy and Climate Research at Jülich, at the research center in Jülich, and has many positions, and among others, he is one of the coordinators of the Copernicus project on Power to X. And I'm very much looking forward to your presentation. The floor is yours.
Kurt, many thanks for the kind introduction. Many thanks for the organizers giving me the opportunity to present some of our results. So I'd like to continue the discussion that Peter Dröll and Jens Nørskov had started. So I'd like to talk about a circular CO2 economy. And I'd like to highlight one of the technologies. This is what we term Power to X, as a missing link to establish such an economy. So I'd like to start from a climate perspective. So if we consider the calculations, the model calculations by the IPCC, we need a certain toolbox in order to achieve that the increase of the surface temperature remains well below 2 degrees centigrade. And this is what we see on the left-hand side. And there's pretty much consensus that we need traditional mitigation technologies where we have to directly electrify key sectors like the energy sector, like the mobility sector. And this is indeed a decarbonization strategy. So we feed in renewables directly into these sectors. But we will only reach this goal. And this is what you can observe in the lower part of the left-hand figure, if we also come up with CO2 negative technologies. So, which means our toolbox not only has to contain direct electrification elements, but we need technologies to indirectly electrify sectors like the transportation sector, like the chemical industry sectors. And here indeed, and this has been made the statement already by Kurt Wagemann, here we need a defossilization strategy, or I like the term also mentioned by Peter Dröll, if we talk about a circular economy, we need a recarbonization strategy. And indeed, this is what we are doing in the project that has been mentioned already. I hope that the slide, so I encounter some problems with switching forth and back with my slides, but this indeed is where research in Germany is done in a national flagship project, what we term Copernicus. So Copernicus, the name is because it involves a shift of paradigm. And this is where we concentrate forces from the most important academic partners in Germany dealing in this area together with the industrial partners, but we also include partners from the society, which means the technologies that we want to develop in the field of power to X have to be not only efficient and technologically perfect technologies, but they have to be also accepted by the society. And in this project, we follow two different technology pathways. So the one is a green hydrogen pathway, where we start from renewable energy and we feed in this renewable energy along different valorization pathways. But we also have a second technology pathway where we follow an electrochemical valorization of CO2. So now if we compare these different pathways, the green hydrogen is a pure linear value chain, which means we start with renewables, we use electrolyzers, we can store it intermittently, we can re-electrify it by fuel cells, and then we can feed it into the energy sector or the mobility sector. Now, if you want to tackle the challenge of a circular CO2 economy, we need a technology which has been outlined already by Jens, where we can use renewable electricity and we can have an electrolyzer that deals with an electrochemical reduction of CO2 to carbon monoxide or to syngas, and then we really can close the carbon loop by producing platform chemicals or circular fuels. Now the question is, what is the CO2 source? And in this respect, we can distinguish between two different future CO2 sources. And so now if we follow this feedstock transition as been outlined by the European Green Deal initiative, we can, if we consider the right-hand graphics, we can either use industrial point sources beyond coal incineration or something, and then we can collect this CO2 and we can feed it back into chemical production. And then we have a closed circle, and then we can talk about real CO2 neutral production. Now, this will be one future CO2 source, but the question is, can we become even CO2 negative? And the answer is yes, we can do so. If we can leave nature doing part of the work, which means if we consider biomass as a scalable, available CO2 source, and then if we feed in, for instance, by a biogas plant, the biogas into our power to X process, then we can consider a truly CO2 negative value chain. So these are the two sources to be considered by power to X. which means the aim of Power to X is to maintain the existing product portfolio, but with Power to X, we can use CO2 as a renewable feedstock, but we can drastically reduce the CO2 carbon footprint. And by doing so, we can establish a circular CO2 economy, and Power to X adds on, or is one of the toolboxes that we need for recycling strategies. So now if we consider the lifetime of any chemical product, at a certain time, it will come to its end of life. It can be reused, it can be mechanically recycled, it can be chemically recycled, but still there will be some parts of products which cannot be chemically or mechanically recycled. And then thermal waste treatment is the only solution, and thermal waste management is one of the CO2, of the concentrated CO2 sources. And this is where Power to X can close the loop for a 100% efficient recycling strategy. And then it means that Power to X can link different sectors. This is the key technology to bring renewable electricity into sectors where we cannot directly electrify, which means Power to X. X can be heat, X can be fuels, X can be chemicals, and X can be gas for intermittent storage. So now, coming back to our Copernicus project, one of the highlights is a satellite project where industries like Siemens Energy and Evonik have started to demonstrate Power to X value chains. And one of the nice examples is in the satellite project Reticus, where it is demonstrated already on a technological scale that conversion of carbon dioxide to specialty chemicals, and this is close to a business case already, which means we can come up really with demonstration solutions by using Power to X. So now Jens has already outlined that there is a big economic challenge. So now if we want to do something for the climate, we have to work for the largest market available. And this is clearly the power to fuels market. But the challenge here is the biggest because the value is the lowest, the value generation. This is plotted here on the y-axis. So this is why if you want to ramp up these technologies, it might be wise to start with smaller markets where the value generation is higher, such that we can already at an earlier stage of this technology development come into an economically meaningful situation. And this is why we believe that the technology development has to follow a learning curve, because from the electrochemistry, the processes are quite similar. And this is why starting with specialty chemicals, as has been shown on my last slide, and then going to bulk and to platform chemicals, and then finally, if the technology is really ready and scalable, one can use it for the power to fuels market. Technology is similar to the example that I have presented already for the specialty chemicals, which means we use renewable electricity, we use renewable resources, CO2 point sources, biogenic sources, and then we produce by means of electrolysis, we produce syngas. And then we enter the established industrial routes, how you can produce from your process gas by means of Fischer-Tropsch or by means of methanol routes, all kinds of different synthetic fuels. And these synthetic fuels already now might also be used as a blend or as a substitute, which means it can be fed into the value chains in order to help to reduce the emissions of the existing vehicles.
Rüdiger, presently we don't hear you. And you also have to come to the end.
Yeah, I am at the end. I am failing to come to my last slide, but perhaps I can adjust. I just can, yeah. Okay, so now the big question is, where do we get all the energy needed for Power to X? And this is perhaps already the transition to the presentation from Florian Ausfelder. So we need much more electricity than the one we can produce. So these are the numbers for Germany. But I guess this will be true for many countries in Europe, which means we need to think of a global economy, and we need to take advantage of renewable sweet spots where the costs for electricity, for renewable electricity, are low. Perhaps we will produce energy carriers already on spot and transport it to the European countries, which means all the issues are not issues that can be solved in one country, but really we need a global renewable economy. And so thinking about a future energy system, my statement is clear. Renewable electricity is an enabler to a climate neutral industry. We need direct and indirect electrification in order to achieve a contribution from all industrial key sectors to our climate change, to our energy transition scenarios. Electricity, renewable electricity, is a scarce resource. It's not for free. We need to think about global economies, but if we are successful in using CO2 as a renewable feedstock for chemical valorization, we can close the carbon loop, and then we can come up with a circular carbon economy, and this will be the big challenge for the future. Thank you very much.
Thank you very much, Rüdiger. That was a very important contribution also with respect to our panel discussion after the break. And of course, I also like very much the example of the Reticus project, two companies from different sectors working together. And that might be also subject with respect to catalysis, namely the government or the European Commission. I now look at Peter Dröll as a catalyst to bring different sectors together. Yeah, thank you again. And talking about other sectors, that's the subject of Florian Ausfelder, our next and last speaker. He's our spokesperson for energy and climate here at DECHEMA, and he is heading a large team of co-workers. He is expert with respect to the energy system as a whole, and of course also to sector coupling. And he will now talk about the future of the chemical industry. Let's name it in that way. Florian, the floor is yours.
Thank you very much, Kurt. Good morning to everyone. Let's see if I can get my slides, please. Okay, that jumped already. Okay. So last year we were employed by the German Chemical Industry Association together with Future Camp to take a closer look at what would be needed for the transformation of the German chemical industry to make it greenhouse gas neutral. We published a report. Sadly, this report is currently only available in German, but that's why I have the opportunity in this presentation to hear it in English. I will actually start with the results. If you look at that slide on the left-hand side, you see the situation that the German chemical industry is facing at the moment in terms of emissions. And then you see 3 different bars going to the right, and they represent different pathways. But if we stick to the bar on the left for the moment, you will see 3 different colors, which we labeled Scope 1, 2, and 3. Scope 1 is everything that happens within the chemical industry. That is essentially, these are process emissions coming from some of the base chemical processes, but these are also emissions that come from the power and heat generation within the chemical industry. The chemical industry in Germany is responsible for about 10% of the overall power demand in Germany and produces about 1/3 of that by their own power plants. So this is quite a significant contribution there. Scope 2 represents emissions which come from energy services purchased from somewhere else. So these are, for example, electricity purchases that come in from the outside. And Scope 3, and that is new to this report, actually represents the carbon contained in the feedstock of the chemical industry. The chemical industry itself is in the business of actually transforming compounds which contain carbon from mineral oil or gas to what we know as plastics or consumer products. The carbon contained in there is usually not accounted for, and this is the first report that explicitly takes it into account. Normally, these emissions would appear once you incinerate the waste. We now decided to actually contribute it to the chemical industry, allocate it to the chemical industry, and as you can see, it simply doubles the emissions that the chemical industry produces. Then we looked into 3 different pathways. A reference pathway, which is essentially a business as usual. So you see a decline in Scope 1 emissions, which are the dark red ones, due to efficiency measures. You see a sharp decline in Scope 2 emissions, which is essentially the decarbonization of the energy system outside of the chemical industry. And you see no decline in the feedstock, because in the business as usual scenario, we essentially use the same feedstock as we do at the moment. Then we have a technology pathway, and that also produces some significant reduction in the overall emissions. The technology pathway introduces new technologies similar to what Professor Norskov talked about, for example. However, these technologies are implemented when they're economically feasible. And we will see later that actually comes rather late in time. And then we have a greenhouse gas neutral pathway, where the conditions are we implement a technology as soon as it gets a greenhouse gas reduction, no matter what the economics look like. And we force that pathway essentially to come down to greenhouse gas neutrality. You see a few residual emissions. That is because our report focused on CO2 emissions. There are some emissions from other greenhouse gases, which were not explicitly tackled in this report. And therefore, we decided to show them here on that slide, because we haven't abated them, so to speak, in this report. And there need to be some additional measures taken in order to abate them. As mentioned before, essentially we're aiming for CO2 circularity in some way, and this is the way we look at it. From the left-hand side, you got the raw materials coming into the chemical industry, and they enter the base chemicals. And within our report, we actually, in that rectangular that you see right in the center, with labeled with process A, they are the processes which transform the base chemicals. And these processes were treated explicitly within our report. These produce intermediates, which then go into what you see in here as a big black box, which are all the other chemical processes that come downstream. These are a huge variety of chemical processes, so we can't really treat them all explicitly. And from this black box, you finally end up seeing your products, your chemical products, which go out to the consumer or to other industries and enter their value chains. What is important to realize in this picture is, however, that this rectangular box labeled process A is a box where essentially most of the energy demand lies and most of the emissions take place. The black box, which we kind of ignore for the time being, is actually that part where most of the value is created in the chemical industry. And therefore, the challenge lies that if we do mitigation strategies that have to tackle essentially the first box, we have to be able to mitigate the financial impact along the value chain. Otherwise, we won't be able to do it. What comes out of everything is the consumer product, and as I said before, it eventually will be burned or combusted into CO2, and that can in turn be like coming in as a raw material on the lower left-hand side together with hydrogen, and we need electricity for that. We also had to make an assumption that the amount of carbon we export or import is equal, but that is more an assumption we need to close the overall calculation. Good. We looked at quite a few different technologies for the base chemicals, and you will notice that these are all technologies which we labeled with technology readiness level 6 or higher, because these technologies need to be able to be implemented within the next 20, 30 years and actually make an impact. So this is notwithstanding the comments made before about fundamental research, which is very important and can improve a lot. But in order to see a large-scale impact, we have to rely for quite some bit already on technologies which are at a later stage of development. You will notice that the methanol to olefins technologies are missing from that list. This is due to the boundary conditions set to us from the chemical industry that they want to keep and use the existing assets as much as possible, and we don't have any methanol to olefin assets in Germany currently. This is maybe the most important slide, and it looks a bit busy, so please bear with me while I try to take you through it. You see different series of lines in different colors. The black lines represent the conventional process. On this slide, it's the conventional production of ammonia coming from steam reforming of natural gas and subsequent ammonia production. The red lines represent an alternative process, in this case, the process of water electrolysis, producing hydrogen, which reacts with nitrogen, which is produced by air separation. So the solid black line are the specific costs of ammonia production as a function of time for the conventional process if it would be a non-depreciated plant, a greenfield plant, a plant that we would build at that moment in time. The same holds for the solid red line, which is a new plant for the new technology, and you can see the specific production cost. The dashed lines represent the depreciated plants, so brownfield plants that already exist. And the dotted lines that you can see are actually the CO2 emissions associated with each of the processes and how they develop over time. We made an important assumption. Since the chemical industry in Germany is such a huge electricity user, we didn't consider it appropriate to say, oh yeah, we get all the renewable electricity and everybody else has to use a coal-fired power plant. Instead, we use grid electricity. And that is the main reason why the water electrolysis in the beginning actually has more emissions than the conventional ammonia process. So if you look at that, we put in several blue lines to show where there are gates that get crossed when comparing these two processes. So the first one is TRL9 gate. That's the question, when is the new technology available on a large scale? And you can see we put that line at 2031. We can argue about that line, but it's not that relevant. Then the next blue line that we see is a line where we actually have parity in CO2 emissions. So it's only from that point on when the new process is better than the conventional in terms of saving CO2. The third line actually is a comparison between the two non-depreciated processes. So that's a moment in time if you want to build a new plant where both of these plants would produce ammonia at the same specific production cost. And the last line is the line where a new ammonia plant with a new technology actually becomes compatible with an existing plant of the old technology. And that is, sadly enough, the situation we essentially face in Europe and we face in Germany, that we have plants for the basic chemicals which are operational for decades already. They are depreciated. And this is the economic challenge for any company to build a new plant on a new technology. What we also did is we compared the sensitivity of the parameters, and in this case, it's not really surprising, the sensitivity of the electricity price that you put into the system and the model and the price you put in on the fossil fuel are the relevant parameters. Interestingly enough, the CO2 price is not that relevant. And that is due to the fact that you are working against a process which is based on natural gas and therefore doesn't produce that much CO2 because it doesn't contain that much carbon. Okay, we also had a look at plastics recycling, which we see, as Rüdiger Eichel mentioned before, as one of the major components to put or bring in carbon in a circular fashion. We looked at mechanical recycling, which we currently know and do already, and we looked at chemical recycling, which is currently not implemented on a large scale and has the potential to reduce the carbon demand in the chemical industry. I skip over, well, maybe not yet this one. So if you look at the greenhouse gas neutral pathway, we see how the overall energy demand of the German chemical industry develops. And that is one important message. Going to power-to-X processes won't reduce your energy demand. It will increase it significantly. Here you see essentially a doubling of the existing energy demand, which is due to the fact that the fossil energy carriers, which are used at the moment, contain their own energy. While with a power-to-X process, we have to put in the energy in terms of electricity. So that raises also the question, what do we actually consider energy efficiency to be and to look like? Then we have the greenhouse gas emissions, no big surprise there. Essentially, we force the pathway to go down to zero. So that's what you see. The cost structure in terms of operating costs rises also because electricity is and will remain a rather expensive energy carrier that you have to pay for. So as soon as you implement these power-to-X processes, which in our model come into play around 2040, you see the operational cost rising.
Florian, you should come to the end.
Yeah, I will. I just go one slide that is important from our point of view. Emissions, overall emissions. These are the three different pathways that you see on the left-hand side in the graph. And they reach in 2050 a certain reduction. It was 27%, 61%, and 99%. However, if you think of CO2 in the atmosphere as a budget rather than as a fixed moment in time, the question is, how does this budget develop? And that is what you see on the right-hand side. So due to the fact that these technologies, these new technologies get implemented rather late, the overall cumulated emissions stay rather high. So even though we will invest a lot of effort and technology into moving forward and being greenhouse gas neutral in the best case in 2050, it still means that we will emit a significant amount of our carbon budget into the atmosphere until 2050. And finally, I just want to say there is, within the chemical industry, there's no silver bullet. There are a lot of different things which have to be changed. It includes the own heat and power generation. It includes the questions of what is our feedstock. We will have a hydrogen demand, which is very, very large. We will see an electricity demand in the order of the electricity system in Germany. It is not said in that study that this electricity demand has to be met in Germany, but the overall amount of electricity still will have to be provided somewhere. And that's all I want to say for the moment. Thank you very much for your attention.
Yeah, thank you very much, Florian. That provides a lot of input for the discussion. And we are now approaching the break. But let me address all the whole audience out there. You have already the chance to ask questions to us all, the speakers and myself. And I also should warn you that we will also address questions to you. So be aware of the fact that there will be polling during the discussion round. So, as I said, we are now approaching the break, and we will start again 30 minutes past 10 o'clock, 10:30 sharp. So please be with us again.